His name is Harsh Patel. He is a PhD student in the Aircraft Design Lab of Stanford University. Harsh, the floor is yours.
Thank you very much. So hello everyone. Yeah, my name is Harsh Patel. I'm currently working with Professor Juan Alonso, and we are working on performing aerostructural trim design optimization by interfacing SU2 with Nastran and integrating that through OpenMDAO. So the presentation outline will start with just a brief introduction of our guiding research questions and objectives, followed by a brief theoretical introduction and equations for the Aero-Structural-Trim coupled sensitivities, followed by an application of this framework, both in terms of a design test case, the computational framework, and then we'll provide some preliminary aircraft optimization results. So unlike most academic research projects, ours is sort of unique in the sense that we're heavily focused in terms of the industry, and then the framework and the tools we're developing are meant to be industrial strength. And so the questions sort of we're asking is, can coupled multi-physics sensitivity analysis be useful in these types of settings? And in particular, can these types of workflows and frameworks be flexible and modular enough to meet the demands of the industry? So then our objectives can be summarized in three forms: is of course to have nonlinear high fidelity tools like SU2 to perform some of these coupled physics calculations and use those sensitivities for aeroelastic considerations, particularly in the conceptual design phase. And so we want to be able to efficiently calculate these coupled aerostructural trim sensitivities for all necessary cost and constraint functions, which requires incorporating metrics for trim, aircraft stability and control into the optimization process. So here's just a brief few slides on the theory and how we get these sensitivities. So we start with the governing equations of the three disciplines: the aerodynamics, the structures, and the trim, where Q is the vector of your aerodynamic state variables, U are the displacements, and the delta here is the vector of control surface deflections. Compared to the aerodynamics and the structures, the trim equations have very low dimensionality because they're simply just force and moment balances. So they're much easier to deal with compared to the aero and structural disciplines. But combining all of these into a single multidisciplinary system, you get the overall residual that we are ultimately trying to solve for in this case. In general, all three equations are fully coupled. However, the coupling can be stronger or weaker depending on the test case. In most cases, we have a lot more design variables compared to functionals, objective functions of interest. So then we solve this disciplinary system and for the sensitivities with the adjoint approach, as we see here. So we solve this linear system for the adjoint variables here, which we then use to compute the total sensitivities with respect to an arbitrary number of design variables. And this is the most efficient way to do so. And this is what we're in the process of implementing in our framework. So this diagram here summarizes our overall framework for the sensitivity analysis. Our framework will not only enable the optimization of aerodynamic properties based on, say, structural stiffness, but also optimize the aeroelastic stiffness based on metrics of aircraft stability and control associated with those aerodynamic properties. So then the primary objective in our case is to assess whether the structural requirements that we identify for the aircraft serve to optimize the qualities of aerodynamic performance, stability, and control. And that includes considerations for things like flutter. And our application test case that we are currently working with is the Efficient Supersonic Air Vehicle, originally developed by the Air Force Research Lab. This particular model has objectives for supersonic cruise, dash, very high maneuverability requirements, and of course, things like range and endurance. So these mission requirements lead to a tailless configuration with both conventional and non-conventional control surfaces for aircraft stability and control. So here is the model of the ESAV, and this is the half model that we're working with currently for our computations. The ESAV model, because it comes directly from the industry, it is also utilizing structural finite element modeling techniques that are consistent with typical aerospace methodologies, and then the design and engineering processes that we are trying to address in this project. We are also considering multiple flight conditions because a single set of flight conditions rarely defines a design. So adding multiple competing requirements, typically we're targeting 3 to 5 scenarios perhaps, will introduce compromise into the design, but it will ultimately generate a robust wing. So moving a little bit on to the computational framework side, of course, we're using SU2 for the high fidelity CFD. We're also using the mesh deformation solvers that exist within SU2, as well as the freeform deformation features for the aerodynamic shape parameterization. We use Nastran for the structural modeling and the evaluation of trim and aeroelastic responses, sort of building off of the previous presentation as Nicola introduced. The load and displacement transfer schemes are part of MELD. It's part of the Fun2Fem package developed out of Georgia Tech. And then our optimizer is SNOPT. And since everything we do is interfaced through Python, we have PyOpsParse to integrate SNOPT. And all of these various tools are combined into an MDAO architecture through OpenMDAO. So we add the high fidelity corrections from SU2 to Nastran by a series of correction factors. So Nastran by default only has a low fidelity doublet lattice method using just 2D panel meshes, but we can provide a series of connections through these 3 different sets of matrices to alter the lift and the moment calculations. Currently, we're only working with this FA2J matrix, where we provide the delta CP corrections from SU2 after they've been interpolated, and we add them as corrections or offsets to the doublet DLM predictions. So if you were to, here are just some representative results. If you were to use Nastran alone, your pressure distribution may look something like this. And here's for a 0 angle of attack at subsonic, transonic, and supersonic Mach. And here is for a higher angle of attack. So these are just the delta CP pressure distributions using the low fidelity VLM only. But then if we introduce corrections from SU2, your pressure distribution may look something like this. And here is just increasing, and when we manipulate the interpolation parameters. So this is for a transonic case, and here we have the supersonic case. So you can see that the pressure distributions look quite different from the DLM pictures we were just showing in the previous slide, which is good because that shows that what is currently used in industry based on the DLM method may be insufficient in many cases, and it provides value for integrating high fidelity tools like CFD with Nastran for these types of problems. So we are orchestrating this sensitivity analysis calculations optimization through OpenMDAO, which is what is used to compute the sensitivities and the gradients that we want. In OpenMDAO, our model consists of all the various tools, and ultimately we're interested in calculating the total derivatives that come out of it based on some input design variables. But at the OpenMDAO level, we are required to supply some partial derivatives that are handled at the subcomponent level. And the way OpenMDAO is structured, based on the unified derivatives equation by Professor Martins and Juan, they will automatically compute the total derivatives, assuming that the subcomponent level and the component level have the correct partial derivatives defined. So when we put all of these tools together in OpenMDAO, it outputs this nice visual for just visualizing how your model looks and the sorts of different connections and the flow of information that you have put together. So there's not much to say here. Here is just a single scenario, but we can replicate this for arbitrary number of design considerations. So moving on to a representative optimization problem with the framework assembled, we just starting to apply this for actual Aero-Structural-Trim optimizations. But here we just have a weight minimization problem subject to stress constraints, where our design variables are the element thicknesses in the structural model. We start out with an initial uniform distribution on the thickness of 1.5 inches. This corresponds to an initial weight of about 73,000 pounds. And as a constraint, we're setting the maximum allowable design limit to be 40,000 PSI. So considering each individual element would lead to over 20,000 constraints in our model. So we for computational efficiency purposes, we are using constraint aggregation to improve those types of calculations. Yeah, so just here, the next few slides are just going to be some representative results. Here's just some SU2 flow contours. Here we have the surface sensitivities that we get out of the discrete adjoint solver in SU2. Here on the left is for the drag on the upper and lower surfaces, and on the right for the lift. And this is based on, again, a parameterization through the freeform deformation boxes. So in the full coupling of the SU2 and Nastran, we ultimately get a converged trim solution. So here we are seeing plot of the angle of attack as a function of the FSI iterations. So you see, if we look at the blue curve, which represents the angle of attack in SU2, we start out at cruise and steady level flight. And then after a few iterations, just 3 or 4 iterations, we converge to a trimmed state. And the coupling and the forward analysis here is done through a nonlinear blog cost Seidel approach. So this is for a supersonic 1G case. And then this next plot here is for a 9G load condition, also at the supersonic case. And the converged trim angle of attack is about 30 degrees. And also in 3 or 4 iterations, so that's pretty good. Here we see some just normalized stresses, normalized by the maximum design stress. Here for the supersonic case, here transonic case. Here is just the optimized thicknesses. So in this case, there's pretty close to the minimum with some concentrations of high thicknesses, but on the right with the transonic 1G case, all of the design thicknesses were essentially driven to the lower bound of that we set for the design variables. And then just a brief summary of the various other cases, comparing the Nastran VLM predictions with SU2 Nastran coupling. We see the 2 cases are in generally very good agreement. And here's an interesting one where The weight is about the same for the transonic 1G case, but the coupling produces a slightly lower stress structure. But in general, the results are in reasonable agreement. So as part of this work, we've done a lot of work to extend the Python API for SU2. This particularly includes particular focuses on coupling with external structures and potentially externally defined design variables. So this work has been done with my colleague Alessandro Gastaldi. So we've worked to introduce these two new deformation solvers and expose them to Python. And so they're the C deformation driver, but we also have the discrete adjoint counterpart for that. And they are compatible with both the legacy deformation solver as well as the newer one. And that's adjusted depending on the config options that you set. And we've added a bunch of additional methods for getting geometry information, setting the trimmed angle of attack, angle of side slip, and so on. So just to summarize, we are interested in enabling routine aerodynamic, structural, and trim analysis and design optimization. And we're developing a tool that is meant to be industrial strength. The idea is to use this in the conceptual design phases, which requires having some sort of flexibility in the problem setup and solver interfacing to meet the needs of the industry. OpenMDAO really facilitates this, particularly allowing for arbitrary flight conditions fairly easily and automating many of the things like connecting and the data transfers, inputs, outputs, things like that. At the end of the day, we're using these couple sensitivities, Aero-Structural-Trim sensitivities, to provide insight both into the physics, but provide a path to a reasonable design solution. This is particularly good in cases when the coupling physics may be too complex to characterize and where traditional engineering approaches may be inadequate. Thank you very much.
Thank you very much, Hars. Also, in this case, fantastic work. We reached the end of the first session of today. Our program is now that we will enjoy 10 minutes break before we start with the second session. And just a reminder for the audience, unfortunately, we cannot answer all the questions, but please email the questions and we will answer them. The authors will answer them. Thank you all very much. See you soon.